Well, hi all. Welcome to GradStats 2024 Lab Series. And in Lab 8, we're working with One Way ANOVAs. And this is when our categorical predictor has now more than two conditions. So a t-test is no longer going to be sufficient to look at differences between groups. Instead, we use an analysis of variance, or an ANOVA, and because we only have one predictor, it's called a one-way ANOVA. And it conducts an F-test to determine if the differences between these groups are significant and where the differences are happening between which levels of the categorical variable. We're going to be running our one-way ANOVA two different ways, two different approaches. One is using a ANOVA with post-hoc tests, and the other is when we plan ahead, a planned comparison between the levels of a categorical variable. So, materials you'll need are the dataset survey.save and the lab sheet called Lab8 ANOVAs. And in this lab, we're going to do the SPSS Lab first, and then go straight into the JASP Lab. So grab those materials and we will get started. So here I have our lab sheet opened up, and I also have the survey.save dataset with the ID indicated as a nominal variable and all of our totals already calculated. So, and in our lab sheet just gives us the overview of where we're going, the two different approaches we're going to use, and looking at a one-way ANOVA, and the resources you'll need. So when we're looking at a one-way ANOVA with post-hoc tests, this is when we use the ANOVA first to just determine if significant differences between the levels, between these groups, are present at all. And if you have a significant ANOVA or F-test, it just tells us that there are significant differences. It doesn't tell us where. And that's when we would have to run the post-hoc to find out exactly where those differences are occurring. So we're going to work with the research question of, is there a difference in optimism scores for young-aged, middle-aged, and older-aged participants? And this is looking at the variables of total optimism, and where it's been reclassed, age is no longer a continuous here, it's three groups. And the groups they have for us in the data set is that 1 is 18 through 29, 2 is 30 through 44, and group 3 is 45 and older. So looking at those, what we're going to start with is a basic ANOVA. We'll go to Analyze and Compare Means, and then down to One-Way ANOVA. And here we're going to put total optimism in the dependent list, and for the factor we want the age group 3. And here we also want to indicate estimate effect size for overall tests. So that way we'll get the effect size already calculated for us. In post-hoc, I'm going to have you select Tukey right there. And we can continue there. And I'll just check options to see if we want anything here. Let's go ahead and get descriptives. We want the homogeneity of variance test. That's our Levene's test. And then what happens is if our Levene's test is significant and we have indication of a violation for homogeneity of variance, and then we're going to want these backup tests, the Brown-Forsyth and Welch's. So we'll go ahead and select those at this point. Here we're ready to continue, and then paste so that we can take a look at this syntax. Here we've activated our data set. We called for a one-way ANOVA, the outcome by this categorical variable, age group 3. We're going to get the effect size for the overall model, and we asked for a bunch of statistics to be included, and we asked for the Tukey post-hoc test. So I'm going to grab this and run it. And now we have lots of information here, right? We'll take this just one table at a time. In our descriptives, we have just what we said, our descriptives. We have how many were in each group. 147 participants were in the group of 18 to 29-year-olds. We have the mean and standard deviation of total optimism for each of those groups. And that's really helpful for setting up like a descriptives table. Next, here we have the tests of homogeneity of variances. And we're just going to work with the top row here. When we're looking at Levine's test, which is for the homogeneity of variance assumption check, we're really just interested in was the test significant or not. And here with a significance level of 0.475, we can say no. No significant Levine's test, therefore no violation of the assumption of homogeneity of variance. So because we have a non-significant Levine's, we don't have to worry about the Welch or Brown-Forsyth corrections to the ANOVA. So we don't have to worry about that because the Levine's test is non-significant. So now let's look at our model. The model level test is the ANOVA, the F test. And we're seeing that it is a significant test. We have our F-stat, our degrees of freedom, our significance level, and then down in the next table, ANOVA effect sizes, we have eta squared, which is what we use as an effect size for ANOVAs. And our point estimate is 0.021. So we have a significant ANOVA, but we also have a small effect size for that test. And what does the ANOVA tell us? It tells us that there are differences between those three age groups, but it doesn't tell us between which groups are the differences happening. For that, we need to look at additional information. And that's where the post-hoc test comes into play. Now, typically, you might run your ANOVA without the post-hoc test. Then, once you had a significant ANOVA, you would then run it again with your post-hoc. But either way, the post-hoc tests don't matter if the ANOVA was non-significant. So our ANOVA was significant. Our model says there are significant differences between the age groups here in terms of total optimism. So to check this out in more detail, we look at this multiple comparisons test. And what we have is the group and what it's being compared to. So group 1, 18 to 29-year-olds, being compared to group 2, 30 to 44-year-olds, we go across and the significance level there is 0.308. So that is not significant, which means there are significant differences, but they're not between group 1 and 2. So not between the younger and the middle-aged. But we go down to this next row. This is group 1 compared to group 3. And going across to the significance level, this is 0.007, indicating it is a significant difference between group 1 and group 3. So that's where the ANOVA test is saying there are significant differences existing. It seems to be between 1 and 3. And the same areas you can look at in these other rows. Group 2 compared to group 1 is not significant. Group 2 compared to group 3 is not significant. Group 3 compared to group 1 is significant, and group 3 compared to group 2 is not significant. So it's kind of just looking at it in more detail. Now, the trick to One Way ANOVA with post-hoc is that it has more opportunity for a type 1 error when we're multiply testing the same data like this, because we did the test for the ANOVA and then we did these multiple t-tests here, just looking at all of them. So that kind of ups our opportunity for making a type 1 error, finding an effect when there really wasn't one. So they tend to use a higher restriction for these post-hoc tests, which is why we're using Tukey. So that's all of the information for our first one-way ANOVA using post-hoc. What we also want to look at is how does this translate into interpreting and doing our write-up. So I'm going to move back to our write-up here. This is what we went through looking at the output. We only need to use Welch and Brown Forsyth if Levine's test is significant. And our information that we gather out of the ANOVA table to write up our F-stats line and the eta squared effect size. And then here's the breakdown of our post-hoc tests, looking at where, between which groups, which levels, were there significant differences. And now we're to what the write-up might look like. Same as usual, we need to let the reader know that what test was being conducted and why. We're looking at differences in the levels of optimism across these three groups. We found a statistically significant difference in optimism scores with our F-stats line. Let me go back to here. Yeah, I thought so. So 2 and 432, which means that this is incorrect. Right there. 464 and p-value eta squared. Okay. So while achieving statistical significance, the effect size was very small, the eta squared. We looked at post-hoc comparisons using the Tukey test, which indicated mean scores for optimism in the younger aged group, which was the one we can get this information, the mean and standard deviation, we can get that out of our descriptives table, were significantly lower than scores for the older age group, because that's where we saw on the post-hoc that the differences were really happening, was between group 1 and group 3. And which one is higher there? Looking at our descriptives, group 1 was 21.4 and group 3 was 23.0 when we round to the 10th place. So it might not seem like a whole lot, and maybe that's why, even though we got a significant ANOVA, we still had a small effect size. But we let the reader know that there were significant differences between group 1, the younger group, and the older group, which was group 3. The middle group did not significantly differ from either the younger or older age groups. So just breaking it down for your reader, you're giving them the stats lines and you're giving them information, but you're kind of just breaking it down to the take-home message there. Now, different figures or tables that would work well with a one-way ANOVA are going to be like a box plot, because we have a continuous outcome and we have those groups. So you can look at doing a box plot, a descriptives table where you have the 3 age groups and their how many, the mean and standard deviation for total optimism across those 3 age groups. That would be a good table. So you just look for ways to make the information clear and easy to approach for your reader. Okay, next we're going to take this a different way. We're going to look at pretty much the same kind of analysis, but now we're planning exactly between which groups we're evaluating. It's called a planned comparisons ANOVA. So it's still a one-way ANOVA, but now we're selecting how we're comparing those groups up front. This tends to have more power to detect differences or detecting an effect because you're not having it run multiple post-hoc tests. You're telling the system up front what groups are going to be compared. So, and that's the first thing we got to figure out. Like, it's a very similar question. Are participants in the older age group more optimistic than those in the two younger age groups? So the 18 to 29 and the 30 to 44 groups. So first, when we're doing a planned comparison, we have to decide which groups we're comparing. And as you see, the research question itself helps us delineate that. So your research question tells you what you need to set up in terms of doing a one-way post-hoc ANOVA or a planned comparison ANOVA. And the research question gives you that. It says, looking at this group being more optimistic than those in the two younger age groups. It's a different question than what we asked at the first one. So, knowing which groups we're comparing helps us determine how to set up our contrast effects. Now, what are we talking about there? We need to let the system know which groups, and we do it by setting up kind of a balance. We want the comparison between the group we're interested in and the groups that it's being compared to kind of balance out. And we do that by assigning contrast coefficients. What we want the coefficients to do on each side of this is equal out to 0. So if I set group 1, the youngest group, to -1, and I set group 2 to -1, those together would be -2, right? So I need to set group 3 to 2 to balance that out, because if I add all those numbers together, -1, and +2, they equal 0. That's the trick to figuring out what contrast coefficients you need to have in mind. So let's go try this out in SPSS. We want to go to Analyze and Compare Means, One Way ANOVA. And I'm going to go ahead and reset this so that we can do it from the beginning here. We'll put the total optimism in the dependence list and age group 3 in the factor. We want to make sure estimate effect size for overall tests is checked. Next, here in the contrast, this is where we're going to set up that balancing act. Now the trick of it is we need to go in the same order that the groups are categorized as. For example, in our data, group 1, the younger group, then group 2, the middle age group, then group 3, the older group. So we need to keep that in order in mind when we're setting up our coefficients. Here we want to, our first group is going to have a -1, and then I'll add that in. The second group is going to have a -1 and add that in. And then my third group, the older group, is going to have a 2. So we've added these coefficients to those groups, to those levels of the age categorical variable. And notice that the coefficient total is 0 here. That's important. So we can continue here and then go to options. So this is, because it's the same One Way ANOVA, we're doing more or less like the same outcome, the same categorical predictor. We don't need to do all these again. Like, we know that the homogeneity of variance test was non-significant. We have the descriptives already, and we know we don't need to do Brown, Forsythe, or Welch. So we can leave all those off. You can add them on if you want too, but it's fine to leave them off because we're running the same outcome and same predictor. All we've changed is the contrast here, and we're not using post-hoc. So we will continue and then paste. So a very different set of syntax here. This is planned comparisons. And this first one was One Way ANOVA with post-hoc. There we go. Here we're saying we're doing the one way by age group like before, but now we have this line about contrast. And it's good to know that all of this adds up to 0. We're still getting an effect size. We're still getting the other normal information, like how we handle the missingness and stuff like that. So running this, like I said, the descriptives are going to be the same. If we had run the test of homogeneity, that would have been the same. So no worries there. What we'll focus on here is our model test. We have a significant F-test. Again, just saying that significant differences exist. And we have our degrees of freedom, our F-test, our significance value, and our eta squared. But now we're looking here at these two tables regarding contrast. On this first one, contrast coefficients, we can just confirm that our coefficients add up to 0. Everything's fine there. We're good. If it doesn't add up to 0, there's a problem. And then we're into our contrast tests. So this is kind of like looking at, we tell the reader about the full model, and then we tell the reader about the details. So we already have our F-test for the full model. We look at contrast tests to look at what was the difference between group 3 compared to group 1 and group 2 together. And that was our plan from the get-go. We're going to use this top row because we're assuming equal variances. Why? Because we know that the homogeneity of variance test, Levene's test, was non-significant. So we can assume equal variances between those 3 age groups. Value of contrast, that is the mean difference, the average difference between group 3, the one we're interested in, and groups 1 and 2 pooled together. So our mean difference in total optimism was 2.45. Now the test they're using here is the t-test to look at is there a difference between group 3 and groups 1 and 2. So we have what we need for our t-test line. We have our t estimate of 2.69. We have our degrees of freedom. We know the significance is 0.007. And we have a confidence interval, lower and upper, for the t-test. So the t-test could have gone anywhere between 0.66 and 4.24. The estimate we have for the t-test is 2.69. So we need all of that information for our write-up. So let's take a look at the write-up here. This is what we talked about. Okay, A one-way ANOVA with planned comparisons was conducted to evaluate the differences in total optimism scores between the age group of older participants and younger groups collectively. So that's a little bit of a different way than what we were seeing before. The model results were significant, and we have our model information. Now the details. Contrast effects indicated a significant difference between the older group and the younger groups. And there's my t-stats line with my confidence interval for the t-test. However, the mean difference between the groups was quite small. MD is abbreviation for mean difference at 2.45 with a small eta squared effect size. So again, just giving your reader an understanding of what happened, what you found, and different figures and tables that would help with this, the same as before. A box plot works really well for this, and just a descriptives table. Okay, so let's try one more here. What if we were only interested in comparing two levels in a categorical variable? So let's say you have a categorical variable with many levels, but you're really only interested in comparing two of those levels. So, for example, are participants in the older age group more optimistic than those in the youngest age group? So to compare between two levels and leave other levels out of the equation, we want to set the coefficients, set the contrast coefficients so that we still have that coefficients add up to 0 balance, but set to 0 any of the levels that you don't want included at all. So let's try this one out. We're going to set group 1, the younger group, to -1. We'll set group 2 to 0 to leave it out completely, and set group 3 to 1. That way they still add up to 0 here. And what we're comparing is between group 1 and group 3. We'll go to Analyze and Compare Means and One Way ANOVA. Now, it has a lot of the information we already had in there. I'll go to Contrast and remove all of these. And this time I'll put -1 for the younger group, 0 for the mid-age group, and 1 for the older group. And also go ahead and check estimate effect size for contrast so that we have an opportunity to get effect size instead of having to report the confidence interval. Continue here. I'll check options. Let's go ahead and get the descriptive table and these like we had on the very first run, just to have them all together. And then I can paste. Going over to here, you see that the only real difference is the change in the contrast. Now I'm doing -1, 0, 1. And I went ahead and asked for the contrast effect sizes, so that's different. And here's all the stats that we ran on the first one. So cool. And I'm going to put a little note to myself that this is the comparison 1 in group 3. Okay, so now we have a bunch of stuff. We got all the way from the descriptives, the test for homogeneity of variance, the ANOVA. You notice that the model didn't change. The model stayed with the same F test, same degrees of freedom, and same significance level, and the eta squared didn't change. So the model level results, no matter how we're looking at the contrast effects, The model level results stayed the same. The only thing that did change is the contrast tests. So now the mean difference between group 1, the youngest group, and group 3, the oldest group, was 1.6. It's still a significant test at 0.002, but now I have a different t-test stats line. So it's the details that are different. The model itself, significance and reporting of the model level, did not change just because I decided to look at the groups differently. And now that I put, to give me the effect size, I have Cohen's d at 0.36. So very good. We got that information. What would the write-up look like for this? Let's try it. I'm going to arrange this so that we can just get the information and write it up right here. So it's going to start very much the same. I can take a lot of this information. Remember, because the model results are the same, it's just the contrast effects that are different. So I'm going to copy that, place it here, and take a look at it. There we go. So we did a lot here. We ran 3 different one-way ANOVAs. We did one that was just a straight one-way ANOVA looking at the post-hoc test after the fact. And then we also used the approach of planned comparison so that we can balance out the contrast coefficients there and be able to look at one group compared to all the others, or one group compared to a different group, all within the same categorical variable. And we worked on getting the information out of the output and crafting it into our write-up. So that's the 2 approaches that we use towards running one-way ANOVAs, and we're going to do the same analyses in JASP next. So let's go ahead and get those materials together and we'll move on to JASP. Okay, opening up our data set in JASP. As usual, just make sure your variables came in correctly. And we usually would start by doing some descriptives to help the reader know about the data set, and then we narrow down to our constructs of interest. So for our first research question in working with ANOVAs is, are there significant differences in total optimism scores across age categorized into 3 groups? Our first approach to ANOVA, one-way ANOVA, is going to be the ANOVA with post-hoc tests. So some things we want to do to get ready for that is take a look at our constructs of interest here. We're going to want the outcome of total optimism. And here we go ahead and we can see our mean and standard deviation. You can check your graphs for making sure this has univariate normality. And we can also add in our age group 3 to the split field to see the mean and standard deviation for each age group in terms of total optimism. And this is a good place to start gathering information for a little descriptives table. So then we're ready to run our first one-way ANOVA. We'll go to the ANOVA tab and ANOVA in the classical area. And here again, we want to put our dependent variable of total optimism in the dependent variable field and put our age group 3 in the fixed factors field. And this will start populating our ANOVA table to give us information about the test. Now, before we can go with this F-test, we need to check out the assumption of homogeneity of variance, because it might change if we need to make a correction for the ANOVA. So we'll move on down to assumption checks in our input area, and we want the homogeneity test. Now here we can see our Levine's test testing the assumption of equal variation, more or less similar variation, in total optimism across these three groups. Our p-value for Levine's test is not significant, so therefore we did not violate the assumption of homogeneity of variance. Now, if it had been a significant Levine's test, then we would want to get our corrections of either Brown-Forsyth or Welch, which changes our F-test amount, and it changes our degrees of freedom. But we don't have to worry about that on this one because the Levine's test was non-significant, so we don't need a correction for that violation of assumption because we did not violate that assumption. So we're good there. We can also get descriptive statistics so that it gives us a good start on laying out a table of descriptives for the age groups, how many participants were in each age group, and the mean and standard deviation of total optimism for each age group. So then our next thing is that we have a significant ANOVA. We know that there are significant differences between these levels in terms of optimism, but we don't know between which levels. That's why we need the post-hoc test. An ANOVA, a significant ANOVA, only says differences, significant differences exist. They don't tell us where. So in the post-hoc test, in your input panel, we're going to move our age group 3 factor over into the testing window, and it will start building our post-hoc test table down here. Now, this is a little awkward to read. Your first row here, they could do a better job on that first column telling us which groups are being compared, but they don't. So this first row is group 1 compared to group 2. So when we look across, that's the youngest age group compared to the middle age group, and coming over to the significance level, it shows that it is not a significant difference between group 1 and group 2. This next row is group 1 compared to group 3. So 1 to 2, 1 to 3. And when we come across here, we see that we do have a significant p-value that's already corrected for Tukey. And that's what's going on as a correction, because when we test over and over the same data, like we tested it here for the ANOVA, we have 3 tests for pairwise comparisons. It actually ends up being 6 tests, but when we're testing over and over the same sample, we have a higher likelihood of making a type 1 error, because we may conclude that we have an effect that we think is true in the population, but it's really only true for our sample because we keep over-testing it. So what's going on with Tukey is a correction aspect, making it more difficult to detect a significant difference. But we have here on this middle row that group 1 compared to group 3 is significantly different. And then this last row is group 2 compared to group 3, because that's the only one missing now. 1 to 2, 1 to 3. The only comparison not here is on the third row, 2 to 3. and it also was not significant. So in our significant differences that were found with the ANOVA test, the only two groups that are really significantly different from each other are the youngest compared to the oldest. Now, which of those groups had a higher optimism score? We can look back at our descriptives and see that the average for the youngest group was 21.4, whereas the average optimism score for the oldest group was about 23.0, rounding to the 10th place. So the younger group was significantly lower than the older group in terms of optimism scores. Now, one thing that we could use is the flag significant comparisons, but I mean, we can see that that is less than 0.05, so I think we're fine. Let's take a look at this first write-up to see how we get this information into the write-up itself. So as usual, we let the reader know what type of test was being conducted and between what variables, optimism, and 3 groups of age. We let the reader know the results of the test. First, we're telling the reader about the model. So at model level, that's the ANOVA, we have a significant model that says significant differences exist. Then we have to go into details and let the reader know what we found in the post-hoc comparisons. And I worked in some of my means and standard deviations there, but you could have easily put those in the descriptives before, like a paragraph before you got the results. You do want to let the reader know that the younger group had optimism scores significantly lower than those for the older age group. And it's good to let them know that the middle age group did not significantly differ from the younger or the older age groups. They're just right in the middle. Some good graphs and tables, like I said, the descriptives tables right there, like that information right in there, would be great for a small table to help convey your information to your reader. But for figures, I'd say a good figure for this type of test is going to be a box plot, because you can put your continuous outcome on the y-axis and then your groups along the bottom, and you're able to give a good visual for that. In fact, I bet we can even put it like where we put our descriptives with age group and total optimism there. There may be box plots in here. So it's not in basic plots. Let's see, customizable. There they are. Let it work that out. So there's a nice box plot with the 3 groups and what kind of distribution they had on total optimism. So a good way to help your readers see what's going on there. All right, so that's our ANOVA for just with post-hoc. Let's now look at a planned comparison, because what's going on with a planned comparison is that it's more, it's a stronger test, because it's not, Tukey doesn't have to make a correction for it. When you know ahead of time as a researcher that you're only interested in comparing one level of your group, of your categorical variable with the others, or you're looking at comparing just between 2 of those levels, like maybe I have a lot of ethnicities, but I'm really only comparing between African American and Asian, then I can reduce it down and do a planned comparison to look at that as long as my outcome is continuous. That's what we need for ANOVAs, is a continuous outcome. But let's look at this research question that kind of gets a little more specific at this planned comparison. Our participants in the older age group more optimistic than those in the 2 younger age groups. So now I just have a two-way comparison between the older group and all the younger groups together. And that's what that will kind of guide how you work with contrast effects. And what we're setting up there is a contrast coefficient, and it has to balance. The coefficients we put onto these groups has to balance out. So if we want to compare the 2 younger groups to the older group, we're going to need all of this to add up to 0, all of these coefficients. So I'm going to set these 2 with the younger age groups to -1, and I'll set group 3 to 2, because when I add up all those together, -1 and -1 and +2 adds up to 0. So how do we do this in JASP? Well, let's duplicate this analysis, because we're pretty much starting with this anyway. And we can edit this. And then here, I don't need the Tukey. So I'm going to turn off that by moving the factor back over out of the analysis area. And I still have my normal thing. Notice that our F test didn't change. It stayed the same. We still have an F test estimate of 4.64, the same degrees of freedom, the same p-value, and we didn't get, one thing we needed there was effect size for eta. We can get our eta. We can put that on the first one too. This is our eta squared. So there's our eta squared on the first test. And now with our planned comparison, we have our eta squared. And it's the same results. So the model level results did not change, no matter how we're looking at the comparisons between those levels within the categorical variable of age. So that's important to know. Okay, but we don't need Tukey. What we do need is contrast. So we're going to fold that down. And right now it says none. And we need to give it the contrast that we want to do. All of these are different ways of setting up contrast effects. But the one we're going to do is custom. And with that, we'll scroll down, add contrast of, this one's going to be -1 and -1 and 2. So now with those in there, we can see that it did put the contrasts on the way we wanted them. We can see that this estimate here, this is the difference. This is the average difference between group 3 that we were comparing to groups, the 2 other groups combined. So group 3 compared to the combination of group 1 and group 2. The mean difference was 2.45 between those 2 groups. Now, was that difference significant? Yes, it was, at P007. Now, some other things we might want here to be able to report this t-test, like we have the t-test, we have degrees of freedom, and we have the significance value. What we don't have here is the confidence interval for the t-test or the effect size, the Cohen's d, for this t-test. But we can get them. Okay, there's confidence intervals. So we can get confidence interval for the t-test in JASP. It doesn't let us get to Cohen's d here, it looks like. It looks like we can only get to confidence interval for the contrast t-test. But we do have the effect size for the model. So we have everything we need there. we have descriptives, and we have our contrast results, that there's a 2.45 average difference between the older age group and the younger groups in terms of total optimism, and it is a significant difference according to this p-value. Okay, let's look at the write-up on this one. So again, let the reader know what type of test he ran, give them some descriptives info, and here I'm saying differences in optimism scores between the age group of older participants and the younger groups collectively. So you want to let your reader know what you were comparing, especially in this planned comparison. Model results found significant differences between the groups. That's the same model results we had before, but now it changes. Contrast effect results indicated a significant difference between the older group and the younger groups. And here I have the t-test value, 2.69 right there. The p-value of the t-test, 0.7, 95% confidence interval. So, and then however, the mean difference between groups was quite small, 2.45 right there. And the small eta squared effect size, which was on our main ANOVA F-test up top. Okay, so that's planned comparison, and it was between groups, group 3 and group 1 and 2, like collectively. And here balancing out that contrast effects coefficients to make sure they add up to 0 when I wanted to compare one level to all the others. You just got to pick numbers that equal out to 0. Okay, let's take a look at a different planned comparison. This is for if we were only interested in comparing two levels within a categorical variable. So like I said before, if I had two racial groups that I wanted to compare to each other, even though there's 5 in the variable itself, a planned comparison can help us get to that. An example question with our data here: are participants in the older age group more optimistic than those in the youngest age group? So I'm only interested in group 1 and group 3 here. So to compare between two levels and leave the other levels out of the equation, we're going to set the one that we don't want included as 0. Let's try that out in JASP. So I'm going to go ahead and duplicate this one, and then I can rename it because this is between group 3 and just group 1. There you go, so that I can see in my results my title there and know which one I'm on. The model is going to stay the same. It's still a one-way ANOVA with the outcome of total optimism and age group being the categorical predictor here. None of this changed. What did change is the contrast. So I want to update this. I want to compare between the youngest age group. I'll leave those at -1. I'll put a 0 for group 2 because I don't want them in there. And I'll put a +1 for group 3. So this will remove group 2 completely. It's only looking at the comparison between group 1 and group 3. So now let's see what we have in the contrast tables here. The estimate is 1.60 if I round. So the average difference between the oldest and the youngest was 1.60. And was this difference significant? Yes, it was at 0.002. Here's my t-test for it, my degrees of freedom, and I don't get an effect size here in JASP, but I can report the confidence interval. So report one or the other or both, but at least have your confidence interval or your effect size indicated in your write-up for that detail. But everything else stayed the same. What changed was the type of comparison we were doing, and therefore that changes what we are telling the reader about because we're answering a different question. Let's take a look at that one. A one-way ANOVA with planned comparisons was conducted to evaluate differences in total optimism scores between the older participants, age level, and the youngest age group. And I kind of made sure I put in some mean and standard devi there. I might use the same word like age group and age group. Yeah, that's better. Model results found significant differences between these two groups. So our model is significant. I'm letting the reader know that we're only going to be comparing between two. Contrast tests indicated a significant mean difference of 1.60 between average total optimism scores. There's my t-test line. Now, the Cohen's d, I got that out of SPSS. But if I didn't have Cohen's d, I would still put like the 95% confidence interval. And let's see what it was. 0.57 to 2.62. So 7, 2.62. And if I had both of them in here, the effect size would come before the confidence interval. So it would go more like there. If I'm reporting both effect size and the confidence interval, the effect size comes first, the confidence interval goes last. This small to medium effect size indicated some practical significance to the difference in optimism between youngest and oldest participants. And if you didn't have Cohen's d, you would have to do your interpretation statement off of the eta squared. And we do have those cutoffs from Lab 7. I went ahead and pasted them down here as well. So a 0.03 eta is small to medium. Okay, again, like I said, box plots are good for this type of test, ANOVA. And you could build a nice little descriptives table, things like that, or do pie charts or bar charts on, the age groups, or a histogram on the total optimism, since you would do that for the univariate normality check at the beginning. So there's different ways to work in your graphics and your tables. But that's it. We did a lot. We did 3 ANOVAs. It was kind of the same question, just with little variations in it. But an ANOVA with a post-hoc is different than planned comparison, and you can set up that planned comparison in different ways depending on what the question is asking for. So have fun with that, and congratulations for finishing our last lab in our Grad Stats 2024 lab series. Yay!